Good afternoon, students. It is so good to have you in General Chemistry 1 this afternoon. I am so excited. I am so thrilled. I am so honored, and I am so privileged to have you as my students this semester. As we will begin, I want to remind everyone that you are not alone. This is an academic community. Remember to get help when needed. Reach out to university services if needed. Never give up. Keep trying. We are here to help you be ethical, honest, intelligent, and successful scientists. However, at the end of the day, you must be responsible, ethical, and hardworking. As we begin, I always like to reflect on the work of Werner Heisenberg. You know, he was, during his postdoctoral assistantship with Niels Bohr, Heisenberg formulated his famous uncertainty principle. At the age of 25, he became the chair in theoretical physics at the University of Leipzig. At 32, he was one of the youngest scientists to receive the Nobel Prize. He lived from 1901 to 1976. So this should encourage and inspire you, hopefully, that it's possible, no matter how young you are. So, let's proceed. We're going to go straight to, I'd like to begin the lecture discussing the significance of DNA, so I'm just going to go ahead and talk about it. So, for DNA, we know that in this class I tend to ask you what functional groups do you see, which atoms do you see, and why is DNA important. Then we'll give you some time, and we'll give you the opportunity to go through the structure and just think about those answers. Which atoms do you see? What functional groups do you see? And why is this molecule, this polymer, why is it important? Okay, so let's begin. So right now we see that we have nitrogen. We see that we have nitrogen. We have nitrogen. Let me see. There we go. We have nitrogen. Nitrogen. We also have Wait a second, having a few technical difficulties. So let me see if I can adjust something quickly before I continue with the lecture for today. Adjust something quickly. Okay, let's proceed. So we have nitrogen. We have phosphorus. Nitrogen, we have phosphorus. We also have hydrogen. We also have carbon, and we also have oxygen. Yeah, that covers basically all of them we have here: nitrogen, hydrogen, oxygen, phosphorus, and carbon. So those are the atoms that we see. The functional groups that we see, we have the amine. Is the amine there? Is the amine there? Right there. There we go. You have the amine there. See? There we go. And then we also have the phosphate there. And then we have other functional groups, so I'm not going into all that. We have hydroxyls there. And that's as far as I want to go with you today. So why is DNA important? DNA is important for several reasons. One, plays a role in the replication of cells. It plays a role in maintenance and integrity of cellular function. DNA is important because mutations in DNA can cause diseases, can lead to downstream effects such as diseases. DNA is very, very important. It's like the information, the set of instructions, the blueprint for a specific cell. Not every gene is expressed in every cell, and that's a discussion for a different day. But gene expression is very dependent, heavily dependent on the genes, and genes are made up of DNA. So, very important biopolymer. So let me erase, and we'll proceed forward. Let's see. So yeah, DNA is very important. It has contributed to a lot of discovery. You could go into all of the discussion as to whether it being semi-conservative in terms of replication, all those things, but that's not for this class today. So let's talk about the goals and objectives of this class. I'd like to remind everyone of this because it's important for us to keep focus. The goal of the class is to teach the chemistry content in a way that is relevant to the Bahamian student and digestible for their understanding. The sequence is as follows. Understand the fundamental concept A. Practice problems relevant to understanding concept A. Learn more nuanced details about each concept. And practice more complex problems that integrate the details and the fundamental understanding. So today, we're actually going to go straight into our discussion for this lecture. This is previous ideas that we discussed earlier. There we go. So, I've already gone through the discussion in which we drew resonance structures, drew different Lewis dot structures. One of the things I want to do today is I want to emphasize some key ideas associated with resonance and resonance structures. So the resonance hybrid is one of the best qualitative descriptors of the molecule, and it gives us an idea. It points to the fact that electrons are not in one position all the time. It gives us it's a better description, a better treatment of a better it leans closer and closer to a quantum mechanical treatment of molecular structure. It gives us an idea. It points to the fact that electrons are delocalized. It's a good structure, not perfect, but it's a good description. And one of the things I want to emphasize in this lecture today is I want us to look at the resonance structures of nitrate. And so look at the resonance structures of nitrate. So let me, right there, nitrate. I want to look at the resonance structures of, I'll be focused on today in terms of resonance structures, and then we'll proceed forward into molecular geometry, and we'll continue to discuss some more ideas in terms of molecular orbital theory and valence bond theory. So let me erase, and now let's proceed. There we go. So let's talk about nitrate. So nitrate, NO3 minus. So we know when we look at nitrogen is in group 5, so that's 5 valence electron. Oxygen is in group 6, so that's 6 valence electrons. So when we add those up, 18 plus 5 is 23, and then we consider the 1 that comes from the minus charge, so plus 1, and that gives us 24. That's that. So let's just so we have that in mind. So we're counting for 24 electrons. So let's come on this side right there, Let's draw out what we think the structure would look like. So we consider all of our electrons, we take our atom, we place it there, put single bonds between each atom. So NO, NO, let's see, let me just try this a little bit better. Actually, I can do a little better than that, so let me erase. Let's erase that. There we go. And let's erase that. And let's do this. And like this. There we go. Okay, so that's that. We draw single bonds. So 24 minus 2, 4, 6. 24 minus 6 is 18. So we put 1, 2, 3, 4, 5. 2, 3, 4, 5. 2. And then okay. So 6 dots around anything, and that accounts for all of the things. However, accounts for all of the electrons. However, the issue that we have here is that this has a minus charge, rest formal charge of -1. This has a formal charge of -1. This has a formal charge of -1, and this has a formal charge of +2. Though this is a resonance structure, it's not the best resonance structure we can draw, because one of the aims for drawing resonance structures is you want to make sure you follow the octet rule. It's a big chief idea. And you also want to make sure that you minimize charge, minimize formal charge. So that's one, but let's look at another one. So that's one we can draw. But let's look at another one. So let's look at another one. Okay, so this is a better one right here. See right here. This is a good one right here. It has an overall charge of -1, and we've minimized formal charge as best as possible. Everything obeys the octet rule, so we've ticked all of the boxes. So this is a good structure right here. You notice that we were able to draw two structures. You can draw different structures in which you have. So say for example, just keep that structure in your mind. We can draw a structure where we have the double bond here. So that, and then we have a single bond here, and we have same nitrogen still has the same form of charge, but with double bonds change position. So as you can see, that's resonance structure, that's resonance structure, this is resonance structure. There's several you can draw. However, the best structure is one that minimizes formal charge and that obeys the octet rule. And you want to make sure you hit all of those criteria when you're drawing resonance structures. Now we can draw another one, which we have the double bond on the other oxygen. So there, there. Actually, let me not rush this. Let me take my time and draw this clearly. So there you have. There we go. There we go. There we go. There we go. That. There we go. So that's another resonance structure. So we just drew 4 structures for the same molecule, for the same polyatomic ion. We drew 4 different Lewis dot structures. Different in the sense that the positions of the electrons are the position of the electrons between each atom, it's a slightly different configuration, or slightly different arrangement. That's a better word to use. However, or slightly different position. That's a better word to use. But yeah, so we just drew several structures for nitrate. It's famous for its resonance, and let me just note something. When we're drawing different resonance structures, so say we have resonance structure A, resonance structure B, resonance structure C, there we go. So that's how you know that you're drawing resonance structures, as opposed to, so the arrows, these are the arrows for resonance, and these are the arrows for equilibrium. I'm just knowing this because it's important to know the difference. So this is resonance, these are resonance arrows. When we're drawing resonance structures, these are the arrows we use when we're talking about equilibrium. So it's important to just note that difference. But I just want to show that to you all, but let's move on. Let me just erase, guys, and then we're going to proceed forward. Sorry about the background noise. Let me just erase. So it's important, some key ideas that I want you to take away from this exercise. You can draw different Lewis dot structures for molecules that tend to have double bonds and single bonds in the same structure. And it's important for you to know that the best structure, or the best resonance structures you can draw, minimizes formal charge, and it also follows the octet rule. That's the big thing. The big idea is make sure the obeys the octet rule, especially for second period elements, excuse me. Okay, so let's talk about, so this is just, another thing I want to do is, I want to make sure you understand how to study this type of material. Now, some people, when it comes to andragogy, or learning when it comes to adults, some people may promote everyone learns differently and you must just figure it out yourself. I'm going to show you how I study this material, how I go through material, and how am I able to understand it as your professor this semester. So I'm going to show you how I study this material. So we're going to discuss, say for example, so this is going to be a very engaging discussion this afternoon. Say for example, you were given a piece of a pamphlet, or you were given a section of a textbook, and I told you, I need you to study this quickly, study this in about 3 or 4 days, and I want you to come back and I'm going to assess you on this. Say you had a very specific reason to study. So we've established our goal, we've established our motivation, we want to understand rules for resonance forms, and that's the topic, and it has objectives, so we know what should be our what should we achieve, what should we aim for, what should we strive for as we are studying this material. We want to keep these things looming in our mind as to am I doing something that complements to me achieving these objectives. So the objectives are, after completing this section, you should be able to use the concept of resonance to explain structural features of molecules and ions. And then also it says you should understand the relationship between resonance and the relative stability of molecules and ions. So off the bat, the concept of resonance points to the fact that electrons are delocalized. And it points to the fact that Lewis dot structures don't give us the best description, qualitative description as to the arrangement of electrons in a molecule or ion. So that's kind of like an overarching, a general idea or a general answer to that first objective. And then the second objective says understand the relationship between resonance and relative stability. So what is that saying? We understand that delocalization contributes to stability. Delocalization of the electron cloud around the entire molecule contributes to stability, or gives us an idea of stability. It points to the fact that the stabilization or stability of a molecule comes from several properties. But one of the things it comes from, or one of the things that contributes to stability of a molecule, is the fact that you have the localization of the electron cloud. And what is that based in? It's based in Coulomb's law, in which you have a positive charge of the nucleus of the different atoms interacting with the electron cloud. And the more it interacts, the more interactions you have, the lower the potential energy, the more stable the molecule. Systems tend to lower potential energy, and that contributes, or that is another way to say, is tend to more stable configurations, more stable arrangements of the electron cloud. So that's kind of like the overarching solutions, overarching answers to those objectives. But I'm going to show you how I study my material. So let's begin. So let's go through. So the method I want to introduce to you today, if I can just, there we go. The method I want to introduce today is this method that they call survey, question, read, review, and recite. So let's talk about it. So I do this implicitly. The first thing we're going to do is we're going to survey the material. S. We're going to think of the questions in terms of the objectives that we need to achieve when we read this material. So the questions we're going to have in mind are going to be centered around or targeted at the objectives. We're going to read it again. We're going to review it. And then we're going to recite the key ideas that are associated with this piece of work. So SQR, there we go. Survey, question, read, review, recite. So that's how we're going to do this. You can look up other methods if this doesn't work for you, but my goal for you is to understand this material. So let's begin. First thing we're going to do, it says recognizing, drawing, and evaluating the relative stability of resonance. In this case, this is a excerpt from Creative Commons material, the chemistry labor text. So recognizing, let's begin. Recognizing, drawing, and evaluating the relative stability of resonance contributors is essential to understanding organic reaction mechanisms. So that's a big idea. When learning to draw and interpret resonance structures, there are a few basic guidelines to help. It says there's only one real structure for each molecule or ion. This real structure is the resonance hybrid. It takes its character from the average of all the individual resonance contributors, or alternative Lewis dot structures. So when looking at resonance contributors, we are seeing the exact same molecule or ion depicted in different ways. Resonance hybrids are really a single unchanging structure. Okay, and don't confuse resonance structures with tautomerism. Anyway, the resonance hybrid is more stable than any individual resonance structure. So we're just surveying the material. Let's see, the resonance hybrid shows a negative charge being shared equally between two oxygens. 3. Resonance contributors do not have to be equivalent. Also, this means the resonance hybrid will be the exact mixture. This means that the resonance hybrid will not be an exact mixture of the two structures. All resonance contributors must be correctly with structures. All resonance contributors must have the same molecular formula, the same number of electrons, and the same net charge. So you also have major and minor resonance contributors. So let's make this more practical. Say I have other things to do. And I need to study this material within 1 or 2 hours. That's the time constraint that I'm given to go through this material. My goal is to get at least a B on this test of this material. So we're making this very practical. I want to get at least a B, because I have other classes I'm studying for. 1. 2, I only have about 2 hours tonight to study, and I'm going to refresh my memory about in like an hour or so tomorrow, within an hour or so tomorrow, and then my test is on the Monday. So for the subsequent days that follow, I'll review this material probably for like an hour or so. So this is my first introduction to this material. So I want to spend about 2 hours. I'm going to condense it for this lecture, of course, but 2 hours I would give a lot to this, my first introduction to this material, 2 hours. So in this 2 hours, the first thing I'm going to do is survey the piece of material. So I'm looking at the material, I'm looking at the main ideas. Typically when people write paragraphs, this goes back to English. Typically when people write paragraphs, the main idea is the first sentence, the topic sentence. So I'm looking at that, keeping that structure in mind as I read. So the main ideas for each paragraph should be in the first sentence or last sentence. The middle portion of the paragraph will give an explanation or exposition as to what is being said for the first or last sentence. So and scientists are very logical in how they write. Typically, they're very logical. They write it with the audience in mind. So we're surveying the material, so we're looking at major and minor resonance contributors, rules for estimating stability of resonance. The resonance structures in which all atoms have complete valence shells is more stable. We're talking about the octet rule. You can annotate and put that on the side. The structures with the least formal charge is more stable. That points to the fact that minimization or minimizing formal charge, having things but not having structures that don't have that many charges. And then 3, the structures with a negative charge and a more electronegative atom will be more stable. So that coincides with chemical logic. The structures with a positive charge and the least electronegative atom is more stable. Very good. That's another idea. The structures with the least separation of formal charge is more stable. Least separation of formal charge is more stable. Good. And the resonance forms are equivalent. That are equivalent have no difference in stability. So we're surveying this material. So this is like a little bit beyond general basic chemistry in terms of some of these ideas, but we're only studying that which is relevant to us for general chemistry. So we just surveyed the material, so let's read through it. Recognizing, drawing, and evaluating the relative stability of resonance contributors is essential to understanding organic reaction mechanisms. So as we're reading this, we're going to annotate. So let me get the highlighter. I'm going to highlight first. Some people are proponents of highlighting, some people are not. The reason why I'm highlighting is because when we review, we're highlighting the main ideas, and we're going to annotate based on what we need to associate with that main idea to memorize it. So let's highlight. Okay. So before we get to that, let's make this a little bit. There's only one real structure for each molecular ion. That's something we're going to highlight. Bam. Only one real structure. And what's that structure called? That is the resonance hybrid. So remember, our objective is to understand the concept of resonance, to explain structural features of molecules and ions. That's the first goal we need to achieve. That's the first objective we need to fulfill. So resonance hybrid. Resonance hybrid. So that. Okay. From the average of all individual resonance contributors. So that's that. Look at that. Some people are proponents of rereading. I'm a proponent of rereading. Repetition is good in my opinion. Some people believe you should just read through material, come up with a set of questions, form a guided inquiry, and then practice going over those questions and over and over again, and do it with spaced repetition and all those other good stuff. That's good if it works for you. If it doesn't, you have to come up with an alternative method to study, and this is what works for me. And I hope it contributes to your method of studying. You have to be strategic. What are you going to do to learn best? and the material as best as possible given the time constraints and resource constraints. So let's go through it. There is only one real structure. We have that. One real structure. The structure is the resonance hybrid. And it takes its character from the average of all individual resonance contributors. So you have contributors to the resonance hybrid, and the resonance hybrid is the only real structure. So if I was annotating that, the main thing, if I was annotating that, let me see. Let's see, text. There we go. So let's annotate this. So if I was writing on this, it would be real structure. Let me just drag this over a bit. Real structure, resonance hybrid. So that would be my first annotation I would put there. I'll put that right on the side there, right there. That's like the big idea. And then I would do a next annotation right here, I'm showing you how I study. Okay, so that's the first annotation, and then this hybrid is based on contributors. Those contributors and contributors. Both of the hybrids based off contributors. Contributors are Lewis dot structures. Actually, let's just say Lewis dot structures. Lewis dot structures. There we go. So that's that. And I'm going to take that and do this. Let's just make this just a tad bit smaller. Structures. There we go. That's the first annotation right there. So let's keep reading. So the resonance hybrid is more stable than any individual resonance structures. So let's see. Resonance hybrid is more stable than any individual resonance structures. So that's another idea. Resonance hybrid is more stable than any individual resonance structures. That's our second main idea. So what am I going to do? I'm highlighting. See, I'm engaging. I'm actively reading the material. Not just passively reading it. So let's put in. That's our second idea. And what's that point to? Delocalization. So we want to put it in right there. Why is it more stable? The first thing I associate with that stability, the localization. And I'm going to, let me see if I can decrease the font size. Actually, let's just put that right here. So localization, because that's a big idea. So when I come back to this material on the second or third or fourth day, I have a mind map. I have a place for this material. I've associated with a framework that I already have in my mind from previous ideas, previous discussions, previous concepts. The localization and Coulomb's law. Coulomb's law. And we know, just to further develop the positive and negative. Lower potential energy. So let me see if I can decrease the size of this. Select that, and let's see if we can decrease the size of that. Let's just do that like that. Yeah, so localization, potential energy. Okay. So that's that. So let's keep going. Okay. So we have our second main idea. This is our first reading. First reading. Okay. So let's keep going. Often resonance structures represent a movement of a charge between two or more atoms. The charge is spread out. So that points at the localization idea. spread out amongst these atoms, and therefore more stabilized when looking at the picture above. Resonance contributors represent the negative charges as being on one oxygen or the other. See, we're further explaining that main idea of it being delocalized, of it being more stable than any individual resonance structure. We're further developing that main idea from the first sentence. In the resonance hybrid, the negative charge is spread out. See, we're still rehashing that same idea of delocalization. Let's go to the third point. Resonance contributors do not have to be equivalent. Okay, so what does that mean? What is that equivalency, or what is that weighting coming from? It comes from the further ideas we'll discuss in terms of how does it really obey the octet rule? Does each atom have an octet? Does each atom have a complete valence shell? 1. 2. Do we have as less or least as possible? Do we have minimal separation of charge? Have we minimized formal charge? Those types of ideas contribute to the weighting of the resonance structure or resonance contributor to the resonance hybrid. So resonance contributors do not have to be equivalent. It's another idea. So what's that pointing to? It points to, let me erase that. It points to the rules that we'll discuss further on. So just keep that main idea in mind. So you have to come up with a framework. You have to come up with a structure that works for you. If you find that your study material is not as engaging, try to find engaging material. There's a lot of free material out there if you have access to the internet. Okay. All resonance contributors must be correct Lewis structures. So that goes back to an idea we discussed earlier. So actually, let me erase that. Highlight them. All resonance contributors must be correct Lewis structures. So that's the rules for drawing Lewis structures. And then let's go to the next idea. See, we're trying to maximize time now. Maximize our time, the amount of learning that we're able to do within a specific time frame. All resonance contributors have the same molecular formula. Yeah. Same molecular formula, and same number of electrons, and same net charge. That's that. I'm not dealing with isomers in this class. Not in general chemistry 1. Okay, that's that. So the same molecular formula, same number of electrons. Okay. Same number of electrons and same net charge. So these are what contribute to how we weight these things. It being a correct Lewis dot structure, it having the same molecular formula, same number of electrons, same net charge. This is the guidance that we use when we're determining whether this is even a proper contributor, whether it's even a contributor to the resonance hybrid. So let me see like that. There we go. The highlighter, and that idea, and then that idea. It's that. So that's kind of how I would approach this first page. I hope you see the trend here. We highlight our main ideas, we annotate based on the framework that we have in mind, the previous concepts that we've already gone through, how we can map this on to achieve objectives 1 and achieve objective 2. Hopefully you see what I'm saying, hopefully you understand. If you have any questions, feel free to email me. However, that's what I want you to understand. and we're going to move forward with the lecture today. Okay, let me see. There we go. Let's move forward. Least formal charge, we do the same thing again, just use the associative framework that we have in our mind based off the facts and ideas we've already discussed. So these are more rules for determining resonance, just keep this in your mind. Okay, so let's get to the topic for today, the discussion for today. Okay. Lecture attendance is mandatory, folks. Class assignments are placed on the online platform. We go through this. Office hours occur via Zoom on Mondays and Fridays. Try not to fall behind to make the class for you a more enjoyable experience. Okay, you have an exam coming up on October 26th. So let's talk about Lewis structures and molecular geometry. So we're in chapter 9 in Chemistry Essential Science. I want you to be able to understand and describe three-dimensional shapes of molecules using the valence shell electron pair repulsion theory. It's also called the Gillespie-Nyholm theory. Determine whether a molecule is polar or non-polar based on its geometry and the individual bonding arrangements. Be able to identify the hybridization state. So hybridization is just referring to mathematical mixing of orbitals. That's a short and fast way to describe it. It points to the fact that it points to an idea in the valence bond theory. Be able to sketch how orbitals overlap to form sigma. The sigma comes from the shape and also the fact that on the internuclear axis, sigma and pi perpendicular to the internuclear axis, perpendicular. Pi bonds, be able to explain the concept of bonding and anti-bonding. So bonding is going to come from the fact that when you have constructive interference occurring with atomic orbitals, that results in a bonding molecular orbital and anti-bonding. When you have destructive interference occurring between molecular orbitals, that results in an anti-bonding molecular orbital, and atomic orbitals equals n molecular orbitals. So the same number, it's conservation of atomic orbitals. Be able to draw molecular orbital energy level diagrams and place electrons into them to obtain and understand electron configurations of diatomic molecules using molecular orbital theory. And as we'll discuss later on, S&P mixing, that gives you an idea, that points to some stability in which the way you arrange that energy level diagram changes as you go between two different atoms or two different diatomic molecules. We'll get into that later. Understand the relationships among bond order, so bond order, bond strength, and bond length. So let's continue. What is bonding? Why is it important? What are the types? And what types of elements tend to participate in the different types of bonding? So bonding is a theoretical construct that involves the attraction of the electrons of an atom to the nucleus of another atom. It's important because it provides a foundation for chemical reactivity. Bonding occurs as a means for elements to share, attract, or distribute electrons in order to become stable. You have three types of bonding that we are going to discuss in this class: covalent bonding, ionic bonding, dative bonding. Covalent bonding occurs when atoms share electrons as a means of bonding. This occurs between nonmetals and nonmetals. Ionic bonding occurs between metals and nonmetals. This is bonding between ions, cations, and anions. The bond-Albert cycle gives us a way or a method or a description as to how that structure is formed, how the ionic compound is formed. We discussed that in previous lectures. Dative bonding occurs when one element donates the entire bonding pair of electrons to form a coordinate covalent compound. Typically occurs between metals and ligands. So let's get to the material we want to discuss for today. So you have three bonding models that we want to just introduce in this class. You have the Lewis model that helps us understand and make educated predictions about chemical observations. You have valence bond theory. It provides a more quantum mechanical treatment of the electron, but not as delocalized along the entire molecule. And then you have MO theory, which is like the creme de la creme for this class. It provides a full quantum mechanical treatment of the molecule and its electrons as a whole. Lewis model is named after Gilbert and Lewis, and you have the valence electrons represented as dots. Your electrons forming your bonds represent as sticks. You have chemical symbols to depict the molecules. So let's just go through this again. One thing, so note, place, subtract, intro, or minimize. So NP-SEM, NP-SEM, SEM. So note the total amount of valence electrons, place single bonds between each atom. So let me make sure you understand what I'm saying. Let me make sure. P-SEM. NP-SEM. So note, place, subtract, intro, or minimize. Note the total amount of valence electrons. P, place single bonds between each atom. S, subtract 2 electrons based on the number of bonds added. E, ensure each atom has an octet. Exceptions are with atoms with expanded octets occurring in the 3rd period, and also exceptions occur with your incomplete octets, for example with boron and beryllium. Then you minimize charges. These are the ways you draw really good Lewis dot structures, really good contributors to the resonance hybrid. So let's keep going. Let's keep going. Okay, so bonding theories help us predict the circumstances under which bonds form and also the properties of resultant molecules. Chemical bonds form because they lower the potential energy between the charged particles that compose the atoms. Metals and nonmetals result in ionic bonds. Non-metals and nonmetals typically result in covalent bonds. And metals and metals typically result in metallic bonding. So we've already discussed how to do electron configurations. We've already discussed the bond-orbital cycle. So let's get to what we want to discuss for today. So in terms of common polyatomic ions, I will want you to understand the really, really common ones, and I'm going to, for this class, so for example, I want you to know your perchlorate. I want you to know permanganate. There's a minus charge. I want you to know sulfite. Let me just a little bit better. Okay, so I want you to know. Here we go. I want you to know chlorate. I want you to know perchlorate. I want you to know permanganate. I want you to know sulfite. I want you to know sulfate. I want you to know cyanide. I want you to know ammonium. I want you to know phosphate. I want you to know nitrate, hydroxide. That's the thing we talk about a good bit. Carbonate, bicarb, and that's as much as I want you to know. So, erase. Here we go. There we go. Let's keep going. Okay, let's go. We already discussed resonance. So let's talk about VSEPR. So VSEPR, valence shell electron pair repulsion theory. Big ideas. You minimize repulsions between electron groups, and you maximize distances, and you want to maximize the bonding interaction. So let's keep those big ideas in mind. Minimize repulsions between electron groups, maximize bonding interactions, maximize distance between those things, and you want to keep those things in mind. So linear beryllium chloride. So say for example we have this is a classic example of a linear molecule. I'm using a model kit. If you don't, or if you can't afford a modeling kit, you can use gumdrops, you can use styrofoam, you can use anything or gumdrops and toothpicks. You can do a lot of things with gumdrops and toothpicks. And you can use toothpicks as the bonds and gumdrops as the different atoms. But I'm using a modeling kit for this lecture video this afternoon. So this is beryllium chloride. This is a linear molecule. We can also use this a shape to describe carbon dioxide. However, in carbon dioxide you have double bonds. Okay, so trigonal planar. Boron trifluoride. Trigonal planar. Trigonal, in one plane. Trigonal, planar. Or a better way to draw that, because that's not a better way to do that. Trigonal planar. There we go. Trigonal planar. Trigonal, one plane, trigonal planar. Okay, so let's talk about methane. Methane, tetrahedral. See? Tetrahedral. There are 4 faces. Tetrahedral. Okay. PCl5, trigonal bipyramidal. Trigonal bipyramidal. Trigonal. You have your trigonal face right there, and it's bipyramidal. Okay? Then you have your octahedral shape. There you go. So octahedral. Yeah, this is going to work. There we go. Octahedral. I just want you to see the shape of them. Octahedral. See, we have 6 electron groups. 1, 2, 3, 4, 5, 6. Someone pointed out in class that the vertices. So an analogous way to think about this, the vertices in the shape in some way do correspond to the electron groups. So if you keep in mind that if I'm talking about electron groups, and also one thing to always specify when you're talking about molecular shape, do you want the molecular geometry or do you want the electron geometry? Because they can be different at times. Because I can have 3 electron groups, but one of those groups can be a lone pair. And if that is a lone pair, it may not be, so I may have 3 electron groups. If one is a lone pair, instead of it being linear, it will be bent. And we'll get to that later on. So octahedral, for example, sulfur hexafluoride. So all molecules have particular shape. The shapes are determined by looking at the arrangement of electron bonding and non-bonding pairs. Correct Lewis dot structures provide the ability to predict common molecular shapes. We are able to determine molecular shape by looking at the angles and distances between the nuclei and the electrons. Remember, single bonds are sigma bonds, double bonds are sigma and pi, triple bonds and sigma are sigma and 2 pi. So that's kind of pointing to MO theory concepts, MO theory ideas, but I just want to expose you to it now. So this is a link you can use to look at simulations from Oxford University. So questions to consider when assigning molecular shape. Let's just go through these questions. So for those who do inquiry as they read, do we have the correct Lewis dot structure? How many bonds do we have? What type of bonds are they? And remember, single bond, double bond, triple bond, lone pair, all of those fall under the umbrella. They fall under the umbrella of an electron group. Single bond, double bond, triple bond, lone pair, or non-bonding pair. In this context, those terms can be interchangeable. Non-bonding pair, lone pair, fall under the umbrella of electron group. So how many electron pairs are non-bonding pairs? Where are the non-bonding pairs? Let me show you. We keep on talking about these non-bonding pairs. Let me show you. So say, for example, we had some molecule. Say we had water. This is water has 2 lone pairs. Okay, water has 2 lone pairs. So say I said I want the molecular geometry of water. Let me show you a classic example of this. So I said I want the molecular geometry of water. So look right here. Let me narrow this into you. So this is an example of me building it. It's going to be V-shaped or bent. However, so this is a molecular geometry, it's a geometric shape. However, the number of electron groups that we have is 4. You have 4 electron groups in this thing. So it's important for you to specify, do you want the electron geometry? Do you want the molecular geometry? Typically, people want the molecular geometry, they want the molecular shape. So this is what we're referring to here. It's bent, but it has 4 electron groups. So just keep that in mind. Let that question loom in your mind. So, more questions to consider. Where are the non-bonding pairs? Because if they're not on the central atom, or the atom that really determines the shape of the molecule, it's not going to be heavily considered, at least for the particular question you're looking at. Are there deviations from this ideal description? So valence electron pair repulsion theory allows us to understand molecular geometry. In VSEPR, that's a short way to say it, VSEPR, we arrange electron pairs to minimize electron pair repulsions and maximize distance and bonding interactions. So this is what I'm showing you here. So say we have 4 electron groups, but 2 are lone pairs, 2 are atoms, 2 are single bonds, 2 are lone pairs, 2 are single bonds. This is an example of water. Or sulfur dichloride. Against that. So let's look at another one. Another one, say for example, we had, so this is an example of an octahedral one in which we have 6 electron groups and 6 are single bonds. However, say we had 2 of those electron groups as lone pairs. 1, 2. So we would have something that's square planar. Let me just show you. So the power of being able to build it yourself. Learn by doing. This is for those who are proponents of that. Learn by doing. So see? Square planar. Square planar. It's in one plane. See? It's in one plane. One plane. Square planar. Square planar. However, it has 6 electron groups. The power of building it yourself. When you build it yourself, it makes a little bit more sense. You're able to flesh out the concepts more. So that's what we're pointing to in this lecture today. So we can have 6 electron groups and it can be T-shaped. So that means you have 3 lone pairs. 3 non-bonding pairs. I'm going to use the same color for these so that we know what we're referring to in this. That you can have different colors for your lone pairs. Not in actuality, I'm talking about for the modeling kit. So say we have 3 non-bonding pairs, and it's T-shaped, but we have 6 electron groups. So another way for us to phrase this: find the number of electrons the central atom normally has in its valence shell. Add 1 electron for every atom that the central atom is bonding to. This is just one way to go through it. Or you can remember, the main idea I want you to take away from this is arrange electron pairs in the correct shape. Okay, so in terms of repulsions, lone pair, repulsion for this discussion is greater than bonded pair to lone pair, which is greater than bonded pair to bonded pair. The main idea I want you to take away from this discussion is use the proper rules, use the correct rules to draw your Lewis dot structures. And when you do that properly, when you write good Lewis dot structures, it can help you make or write and understand good resonance contributors. And from those good resonance contributors, you can determine the resonance hybrid. That's one thing you can do with a good set of Lewis dot structures. 2, when you draw the correct Lewis dot structures, you can apply that Lewis dot structure, use that Lewis dot structure to understand the molecular shape, or predict to a certain extent molecular shape. It may not correspond exactly with what we see, and that's the reason why we have to use valence bond theory. For example, with hydrogen sulfide, you have deviations from it. Instead of it being completely linear, you have deviations. So hydrogen sulfide, or instead of it being tetrahedral, whatever the case may be, you have deviations. Whatever geometry you're referring to in this case, molecular shape or electron geometry or molecular geometry, you have deviations. But when you draw correct Lewis dot structures, you are able to understand molecular shape, you are able to determine good resonance contributors and look to see or approximate to what the resonance hybrid would be. It's a very useful tool, and also in organic chemistry, we know that when we draw good Lewis dot structures, we can kind of give a description as to what's occurring, the mechanism, as to how the reaction is occurring. So Lewis dot structures are very useful. Okay. So VSEPR is based on the simple idea that electron groups, which we define as lone pairs, single bonds, multiple bonds, and even single electrons, repel one another through Coulombic forces. So you want to make sure you're looking at the central atom. So valence bond theory. So say for example, remember we talked about this conceptual baton passing, in which we had Max Planck passing it on to Albert Einstein. Actually, excuse me, we had Niels Bohr. We had Max Planck passing it on to Albert Einstein, and then you had Einstein passing it on to Niels Bohr, and then we had Niels Bohr passing it on to Werner Heisenberg. So what I'm saying is typically a way for you to process the concepts. So same way we did that for this thing, we could go from Lewis dot G.N. Lewis dot structure, say if Lewis dot structure was the concept, the main idea, the person with the baton, passing it on to valence bond theory, and then valence bond theory passing it on to molecular orbital theory. This is a way to process the concepts so that you can build on it if this works for you. Okay, valence bond theory is a more advanced theory on which is an application of a general quantum mechanical approximation method called perturbation theory. We're not going deep into that. This is not quantum mechanics class. Just want to expose you to it. So in many cases, these orbitals are just s, p, d, and f. In other situations, the orbitals are hybridized. VBT, valence bond theory, we calculate the effect of these interactions on the energies in the atomic orbitals. So when we apply valence bond theory to a number of atoms and their corresponding molecules, we arrive at the following general observation. The interaction energy is usually stabilizing or negative when the interacting atomic orbitals contain a total of 2 electrons that can spin pair with opposing spins. So a chemical bond is a result of the overlap of 2 half-filled orbitals with spin pairing of the 2 valence electrons. And then also the geometry of the overlapping orbitals determine the shape of the molecule. So VSEPR predicts that dihydrogen sulfide, this is what I was pointing to earlier, has a bond angle of 109.5. But VBT excuse that it should be 92 degrees, not 92 degrees Celsius. Predictions coincide better with experimental results of a bond angle of 92. Okay, so that comes from the fact that VSEPR gives us an idea, VBT gives us a better idea. A further or more complete explanation. That's a better way to put it. So VBT accounts for the bonding of methane and other polyatomic molecules by incorporating an additional concept called orbital hybridization. So hybridization, the mathematical mixing of atomic orbitals to form hybrid orbitals. This is where you get these ideas of SPDF or SP2, SP, SP3D, SP3D2. That's referring to the mixing. So it's a mathematical procedure in which standard atomic orbitals are combined to form new hybrid orbitals that correspond more closely to the actual distribution of electrons in the chemically bonded atoms. A chemical bond is the overlap of 2 orbitals that contain 2 electrons. The greater the overlap, the stronger the bond and the lower the energy. In hybrid orbitals, the electron probability density is more concentrated in a single directional lobe, allowing greater overlap with orbitals of other atoms. So we're going to just keep on going. Hybrid orbitals minimize the energy of the molecule by maximizing the overlap in a bond. So this is like hinting to or based in the Coulomb's law, ideas from Coulomb's law. So let's talk about MO theory. So this is just an overview. This is just introduction. So this lecture is like the introduction to these ideas, and you have to go and do your readings, go and practice the homework. So you play a part, I play a part in this learning process. I help to facilitate, we break up the ground, we help with conceptual ideas forming, helping you see where you can put in your associative framework for learning and andragogical ideas, and then you are able to apply the concepts. You are able to associate it with something you know, and you're able to learn it and flesh this out and make this more real to you. Develop your scientific intuition, all those things. Use these as ideas you can apply in your classroom, apply in other research settings, all of that. So MO theory, this is just an orbital diagram. We have a sigma, sigma star, sigma referring to a bonding orbital, sigma referring to a bonding orbital, sigma star referring to antibonding, sigma, and you have a pi, pi star, sigma star. In MOT, we do not actually solve Schrodinger's equation or molecule directly. Instead, we use a trial function, an educated guess. The trial function we use in this case would be LCAOs, linear combination of atomic orbitals. However, no matter how good our guess, nature is the best at minimizing the energy of the orbital. The simplest trial function that we're going to use in this class is LCAOs, linear combinations of atomic orbitals, which is basically a weighted linear sum of the valence atomic orbitals of the atoms in the molecules. So this big idea that I pointed to earlier, n atomic orbitals equals n molecular orbitals. Sigma orbital, the name is derived from the shape and position on the internuclear axis, and pi orbitals, the shape and position, name is derived from the shape and the position perpendicular to the internuclear axis. So antibonding orbital, you have destructive interference results in MO higher than the energy for the atomic orbitals. This MO is an antibonding orbital. Bonding orbitals are derived from the constructive interference that occurs with that results in a MO lower in energy than the atomic orbital. This is your bonding. And then the bonding MO. So bond order is 0.5 in brackets. You look at the electrons in your bonding molecular orbitals minus the electrons in antibonding molecular orbitals, and you multiply that whole difference by 0.5. So this is what I was pointing to earlier. I want you to take note of this. Take note of this. You see, as you go from diatomic nitrogen to diatomic oxygen, you have a switching. You have a switching of the order. So you go from pi 2p to sigma 2p, and then for oxygen, diatomic oxygen, you go from sigma 2p to pi 2p. So where's that come from? We're not going into a deep quantum mechanical explanation for that. This is a general chemistry class. What we're going to do is get the main idea, get the short summary, condensed answer for that question. Why does the order change? The bottom line is that S&P mixing is significant in diatomic boron, carbon, and nitrogen, but not in diatomic oxygen, fluorine, and neon. That's the surface level. That's just what we're going to talk about for that. So MO theory, let's continue. MO theory helps us understand diamagnetism, in which you have paired electrons, or paramagnetism, in which you have unpaired electrons. And you can see an example of this with supercooled oxygen being held up between two magnets. So those are our references, and that's where we're going to end off our discussion today. Once again, it was so good to have you in lecture today. So good to see you. So good to know that you're in my class. Excited to have you in my class. I want everyone to know that you're not alone. Keep up the work that you're doing. Keep pushing. Keep going. We're cheering you on.